Hi, just gonna go through some comments on homework 10 for your benefit. Um, the problem in the book about all the different energies, that one was fine, pretty much. If you want to know the specific values for one of the answers, you can just send me an email about that specifically. For 5.8 with the proof of the Gibbs free energy, um, a lot of us kind of just wrote down the answer, didn't really derive anything. What you're supposed to do for that one is start from the definition of the Gibbs free energy in terms of the internal energy U, and then you take the differential of both sides of this equation and just simplify until you get to the thermodynamic identity for G. Moving on to question 3 on the back. If you missed any of the parts between A and A through D, then really just kind of review how to do derivatives. Those are derivatives that you could get correct after taking AP Calculus as a freshman. So those first 4 are easy. If you missed ones between E and H, then you really need to look over, watch the video on exact differentials, or at least spend some time Googling that. It's not really the type of thing where I would expect you to like make up what to do for this. But one way that does always work is just to do algebraic substitution. So, for example, on part E, you could write out, A as a function not of x and y, but write A as a function of x and b. So if you did that substitution, then you would get A is equal to 2x squared plus 5 times the square root of x minus b. And then you can take all your derivatives that involve x and b as the independent variables. Basically, you can do E and F, no problem with that. The other thing that's in this problem that was kind of maybe not noticed is that I did want you to re-express all your answers after you get them in terms of x and y. So this is the common theme that we'll see again in problem 5, is that it's very important what variables are there before you take the derivative, but after you finish taking the derivative, then you can do any sort of substitution you want, willy-nilly, whatever you can to make it simpler. It's not really in question 3, it's not really super important what the variables are in the answer, but I did ask you to put them in terms of x and y so that everyone could get the same answers. It was easy to tell if they're right or wrong. Then let's move on to question 5. I think for question 4 it'll be easier to I want to leave question 4. If you got that wrong, go over it again after we've talked about question 5. You can kind of see what's going on in questions 5 and 6 and apply that to 4. So then for question 5, we should have all been able to get to the point of having the expression for U just in terms of entropy, volume, and particle number. So that looks like this. Okay, so that's the formula for U in terms of S, V, and N, and a few constants for the ideal gas with one atom per molecule. Now, if you didn't quite get to this, review your algebra. How do you deal with fractional powers, right? How do you deal with this exponential? When you take it to that 2/3 power, you can multiply inside by 2/3 and get it. You want to get things to the simplest form possible before you take a derivative, because derivative is always going to make things more complicated. So if you take the derivative of something that's already complicated, it's going to get even worse. So try to simplify before that if you can. So the goal here was to take since this is in terms of the natural variables now, u in terms of s, v, and the derivatives don't require any more monkeying around with variables. We can just do them. And so the only place s shows up here is in an exponential, so all this other stuff stays unchanged. Essentially, this is all treated as a constant. Even though it looks pretty gnarly, it's all constants. Even this exponential of negative 5/3. So then the derivative of an exponential is itself multiplied by anything that comes from doing the chain rule. So that's the correct derivative, and this is equal to the temperature. That's the way we get it, treating this as a thermodynamic model based on U. This is the way we get the temperature. You're supposed to kind of verify that this gives you the right expression that we expect for an ideal gas. So this doesn't look so familiar, but again, like we saw in question 3, once you've done the derivative, you can make substitutions however you want. So notice that this is 3 n h bar squared over 4 pi m, the n over v to the 2/3 power, the exponential of minus 5/3, the exponential of 2s over 3nk. This is all just u itself, right? So this derivative, du ds, can be simplified after it's done to be equal to 2u over 3nk. And that's supposed to be the definition of temperature, treating this as a model. So to check this, we could just rearrange it for a formula for u, right? It's going to be 3/2 nkt, which is what we expected for a monoatomic ideal gas. So that's kind of what I wanted you to see. Is, we had this Sackur-Tetrode equation before, but if we treat it as a thermodynamic potential model, then doing these derivatives, it all checks out. I'll leave it to you to work out the one for volume to get the pressure, but just notice that, again, when you do the derivative of u with respect to v, most of this stuff, the majority of the stuff, is just treated as a constant. So you basically have v to the negative 2/3 power. And that's the only derivative you really have to do. You'll get minus 2/3 times v to the negative 5/3 power, and then you have to simplify that down to where you get the formula for pressure. Okay. Then on to question 6. Just a few comments here. Question 6 is really... you're doing the identical things that you did in question 4, except just for a different formula. So the only part here that really tripped some of us up was when we get to the formula for the Helmholtz free energy. It comes out as nkt minus nkt times the natural log of kt over epsilon. So that's a good point. Most of us got to that point, and happy about that. But when you do this derivative, then you're doing df dt. And we can't forget our basic rules of derivatives. So the first term just turns to nk. And then the second term, here's where it's crucial to have it only in terms of temperature. You can't leave a u or an s anywhere in here. It's got to be all t's, only t's and n's allowed. For f. So that's where you see you've got a t here and a t here. So you've got a product rule to do, right? The first one is going to be the derivative of the first term, nk. So your product rule is like this term and this term are multiplied together, and those are both functions of t. So you have nk, which is the derivative of the first, times the log of the second, times the second, which is log of kt over epsilon. And then you have the first, nkt, times the derivative of the second. So the derivative of the second, if you want to do this carefully, is going to be 1 over kt over epsilon, and then times k over epsilon, because there's a chain rule there. So then when you simplify this, you're going to see a lot of this stuff over here, right? A kt there, a kt there, an epsilon there. So this is just going to turn into minus nk, right, which is going to cancel off this first term here that came from the nkt, this first part of f. So it's kind of the clever way that these potentials are set up is usually stuff will cancel out and end you up with something that's a little bit simpler after the derivatives are taken. All right, because this is supposed to be equal to negative entropy. And we knew from the start of problem 6 that entropy didn't have like a sum of 4 or 5 things in it. So those cancellations usually happen just like they did in 6. And, you know, what's underlying those cancellations is basically the same thing that we did in questions 4 and in question 5.8 out of the textbook. Those terms that we add on, they cancel some others off. You know, this one and this one, they cancel so that you get just the middle one left over. Okay, as always, if you have any specific questions on like the answers or parts of the solution that maybe you didn't feel were adequately covered by this video, you know, feel free to communicate with me, guys. It's important, you know, even as you are working through these homeworks, you know, don't spend more time than you need to just struggling, not using the book, not using Google, not using me, right? We're here to be used and you know, provide you that information. And those of you who have asked can verify that I will gladly basically tell you how to do a problem if you ask me about it beforehand. So I'm not stingy, and I'm not going to play games about like you know, like cryptic hints and stuff. Like I want everyone to be able to do these and, you know, get that practice in. So do communicate with me. That's, you know, what we got to do to get through this weird kind of college mode that we're in right now. All right, see ya.